Yeah, delighted to be here talking to Priya about a wonderful book that she's written. I enjoyed reading the book. And I have my cell phone here because I needed to remind me of some questions that I am going to pose to her, and I hope it doesn't bother you too much. While I was reading your book, the first thing that occurred to me was it's beautifully written. And it appeals both to scientists and to lay people. So what led you to think about crafting a book that would appeal not only to the layperson, but also to some of your colleagues in astrophysics and cosmology?
So I'm a deeply interdisciplinary person. I actually have an unfinished PhD in the humanities, in history and philosophy of science. And I've always liked to write, and I never quite understood why there was such a divide between the science and the humanities, and why science seems so inaccessible to the layperson, the interested lay reader. And once my throat, sorry, let me just get some water. And so I started experimenting and writing for the public along with all my research papers, sort of in earnest in like 2014 or so. So I'm sort of the person who reviews science books for the New York Review of Books. And I love that form, that kind of essay that you could bring together lots of ideas, not just focused on one particular discipline, but from all over the place. And then, I was a child, I was obsessed with mapping, and I was always wanting to, I remember my first sort of sharp memory of a book is being like, 4 years old or something, and trying to pick up the Times World Atlas. It was bigger than me at that point, so it was always on the back of my mind that it would be a really fun thing to do, to share the exciting developments in cosmology and astrophysics. As you know, the last century has been incredible in physics and astrophysics. So it seemed like sort of a fun project to do. That's how it got started. And it gave me an outlet, like a creative outlet as well.
Yeah, that's great. I mean, as I was reading the first part of your book, I was struck by the succinct yet enthralling account of the early history of astronomy that goes back 4,000 years. And can you give us a sense of what the major inventions and ideas were during the early part and then in the 20th century?
Yeah, so could we have the first slide, please? So I think what is kind of incredible about the night sky is that we all have access to it, and probably when the first sort of Neanderthals were able to stand upright and look at the night sky, they started imagining and trying to understand, to make sense. They were not quite looking for what we would call an explanation today, let alone a scientific explanation. I think they were looking for correspondences and connections, right? They were seeing all these phenomena unfold on a daily basis, seasonal basis, and they were trying to connect the terrestrial to the celestial somehow. So these are some of my favorite maps, and we don't quite know what these peoples were trying to do, but across civilizations. So one of the earliest kind of depictions of the night sky is the Nebra sky disk, and that was found in the Saxony-Anhalt region in Germany. And then you have the Mesopotamian tablet, the Venus tablet, in which they were charting the positions in the night sky of the planet Venus. And the Mesopotamians already knew the difference between a planet and a star. And then jump forward to the Catalan Atlas in 1375. So they were just trying to make sense and organize the heavens. And of course, as you all know, given sort of our anthropocentric view, the view of the universe at the time was just the solar system, right? We didn't know anything much beyond that. And we knew about the moon, we knew about the fixed stars and the sun. And then there was a question of hierarchically how to organize them. So the Earth was obviously in the center. Till, of course, Copernicus came along in 1543 and changed the pivot. So I think the preoccupation was really, for all this while, pretty much till 1700. It's only after you have Copernicus and then you have Tycho Brahe making sort of detailed observations, trying to really establish the heliocentric view, which then got totally sort of set after Newton came up with the theory of gravitation that gave an explanation for why the solar system is the way it is, and that it was a universal law. So I think that, you know, up to then, we were just really trying to make connections, and then the shift happened 1600, 1700, at least in the West, where the nature of inquiry shifted to one of finding an explanation, and then one that was a mathematical explanation. So next slide, please. So I just wanted to sort of make the point that, you know, although progress was happening in our understanding, it was all very contested. You know, it took a long time for the heliocentric view to actually get accepted. And there's some beautiful maps in which people were depicting, you know, and I think one of the reasons I'm obsessed with maps is that mapping is really a way of knowing, and at least that's the way it's been used in our cultures. And I think you can see the shift from the geocentric view to the heliocentric view just through maps, through our depictions of the night sky.
That's great. I mean, finding our place in the universe from, you know, zooming out from being in a solar system to being in a Milky Way, and then finding ourselves in a universe, and then discovering that the universe wasn't still, but expanding rapidly, that's a fascinating story that you tell so well in your book. Can you walk us through some of the highlights of that journey?
Sure. Could we have the next slide, please? So I think, as I've impressed upon you, at this point, we had really, our universe was the solar system. We knew about our galaxy, so that was known. So it wasn't until 1900 AD that, you know, something really broke loose, and that was the astronomer Edwin Hubble's realization. Could we go to the next slide first and then come back to this one, please? That plate that you see there is of the Andromeda galaxy. So it's the galaxy that is our nearest neighbor, and what you see marked there are some stars, some variable stars that allow you to measure the distance to this galaxy. And finally, it settled a big dispute of whether our galaxy was the entire universe or was there something beyond that. This galaxy was so far away that there is no way it could have been part of our kind of Milky Way. And that sort of set the extragalactic scale, that there is something extragalactic beyond our galaxy. And then if you see the lower panel there, and that he did in 1924. So he really kind of, you know, expanded and opened out our view of the universe, that observation. And then in 1929, he did something, as Sanjay pointed out, something even more radical. He was able to measure the speeds of galaxies. So there were all these fuzzy things in the night sky that he had now established were separate galaxies, different from our own galaxy, the Milky Way. So then he measured their speeds, and he found that there was this pattern. The farther away a galaxy was, the faster it was hurtling away from us. And this was pretty radical, because, you know, the classical notion of our universe across cultures is one of fixity. Everything is fixed, right? And yes, the sun, there are seasons, and the sun, and you have sunrise and sunset every day, but by and large, the cosmos was fixed and it was in balance somehow. So this really was a very disorienting discovery. And the only way to reconcile and understand this discovery was to see that the universe itself was expanding. It wasn't static anymore. So you had to kind of unmoor the universe. And I think this started this trend, which then, you know, as you know, culminated in 1998, as recently as 1998, with the discovery not only that the universe was expanding, but that the expansion rate was actually accelerating. And as you all know, to accelerate something, you actually need energy. So we don't know what it is, but we know how it manifests, and that was the discovery of dark energy. We think it's the agent that drives the accelerated expansion of the universe. So there are many entities now in the universe that we know shape the universe. So this is where we have come to now. We have an exquisite inventory of the universe, so we know that most of the matter, that including the stuff that we are made of, right, is only 4% of the universe. And the majority is actually dark matter, which is not stuff on the periodic table. It's some exotic kind of particle, which is your field of study. And you should weigh in a little bit to tell us what do you think. So what are the likely candidates right now, Sanjay? Because,
Yeah, I mean,
we just call them dark and we leave it there, right? Astrophysicists. So.
yeah, I began thinking about physics at the subatomic scale. And at some point in grad school, I realized that the most fascinating part of this journey was to apply what we understand on the subatomic scale to the largest scales. But the cosmologists, such as yourself, have posed questions that we seem to have no answers to. Discovering that most of the matter was not described by a theory that particle physicists have so dearly put together in the 1970s and 80s, if anything, brought humility to a field that was clearly, going through a phase of gloating and being very proud of having a theory that described everything. And now we know that we nearly everything. And now we know we probably have a lot of stuff that we don't understand. Dark matter and dark energy are certainly key aspects of it. And my own interest is in understanding the most extreme forms of matter and understanding, describing this matter. And when we describe matter on the small scales, Einstein's theory of general relativity, which is a very important aspect of understanding them on big scales, like what you work on, is essential. And in my field, sometimes it is essential and sometimes it's not. So when I was reading your book, what struck me was your description of Einstein as somebody who put together the theoretical scaffolding that basically builds modern theory of cosmology, but at the same time he was so reluctant to accept ideas that his theory itself predicted. And this concept of dark energy was in his theory, but he was reluctant. Can you tell us what that struggle was between his theory that he wrote down and its implications that he did not want to accept?
So Einstein was a really intriguing character, right? Although I'm not one to go for the sort of lone male genius prototype, he was incredible. He was an amazing mind because there's a way in which he had managed to draw this deep, profound connection between the contents of the universe, the fate of the universe, and the shape of the universe. So geometry, he'd somehow connected geometry, motion, and matter. And he sort of completely churned around Newton's theory of gravitation. Part of the problem was Newton's theory of gravitation doesn't actually tell you why gravity works. It tells you what gravity is. It doesn't tell you how it works and why it works. And Einstein really gave us a brand new theory. So actually, Einstein was incredible because, most of us, including me, I have this, when you propose a theory or an idea, you kind of don't want to be emotionally invested, but you are. And you kind of really, you are hanging on to it and you are open to people attacking it, but then you defend it and so on. He, on the other hand, so he had very fixed notions of, this idea of how the universe should be in terms of balance, some sort of, very psychological senses of stability and so on. So when he proposed this theory and Hubble discovered expansion, he said, no, it comes out of his theory. So his theory actually describes that the universe has to be expanding. Einstein's equations actually suggest that. He was a holdout. He said, no, I don't believe this. And it took him a long time till he saw the data accumulating, and then finally, it is said that, at the Wilson Observatory in a seminar room, he finally stood up and said, okay, universe is expanding, and I accept that. But he had the same reaction to black holes. They are a solution to his, this whole idea of the shape of space being connected to the nature of matter and geometry. They are a solution, an exact solution to his very complex 10 equations. They're 10 coupled equations. And he actually thought that these equations cannot have a solution. They're so complex, he thought, they'll be only approximate solutions. But then Carl Schwarzschild, who was then fighting in the trenches, this is 1915, 1916, World War I, fighting in the trenches, but he was a physicist, and he had heard about Einstein's lecture and this new theory, and he worked out, and he found an exact solution, which is, I think we could skip a couple of slides, so you could just show, could you just keep moving? Yeah, this is again Hubble's thing. We can come back to this slide later, but let's go back, go further, please. Further ahead. Ahead. The other direction. Forward, further forward. Okay. Yes. So this is, yeah, okay, this is great. We stop. Yeah, this is, you can stop here and then we can move to the next one. So this is a depiction of the solution, black hole solution. So the black hole solution to Einstein's equations tells you that if you have a very compact, dense amount of matter, it causes an extreme distortion in this shape of space. If you have no matter, space would be flat. And what I mean by space is our universe, and it's actually 4 dimensions I'm talking about, not just 3-dimensional space. 3 dimensions of space and 1 of time, so it's called space-time. So Einstein showed us that the presence of matter would cause that divot. So you saw something like, looks depicted like the sun, right? So that would distort space-time. And remember, we are all living on space-time. There's nothing above it or below it. This is like a schematic, it's a cartoon to show you. Can't quite show you a 4-dimensional object. But if you have a neutron star, which is the kind of stuff that Sanjay works on, they're very dense, they're very extreme objects. They would cause a deep divot, a very deep pothole in space-time. Whereas if you have a black hole that is even more extreme, extremely compact and dense, you actually cause a puncture in space-time. And just if you want to know where do you puncture into, we actually believe that you cannot remain in our universe. You have to actually tunnel to another universe in that puncture. But that's, mathematical. It's not physically proven quite yet. Next slide, please. So this solution of a black hole, this is what Einstein really disliked. The reason he disliked it is this region that I've written and marked as the singularity. That's the interior of that puncture, and that's a point where all known laws of physics break down. So Einstein didn't like that. He didn't like this idea of a singularity at all. The other thing he didn't like is that black holes have this sort of sacred boundary. It's called the event horizon. And that boundary is a boundary from which not even light can escape. So once light goes in there, it doesn't escape out, right? Let alone matter, right? I mean, we would all be spaghettified, pulled by the intensity of the gravity. So if I was falling in head first, I'm really vain about my hair, but anyway, then my hair would be pulled so strongly compared to my feet that I would be stretched out into a spaghetti if I crossed the event horizon. So it's a point of no return, actually. So Einstein just totally disliked this. But you know what? He didn't actually change his mind till the very end, very, very late in his life, when it became clear that it was a legitimate solution, and even if he didn't like the singularity, he was like, well, I guess I have to accept it. But he was a strange scientist in that way.
Yeah, we'll probably come back to this issue of the human aspect of science later on. I mean, I also enjoyed that section of your book where you talked about how science is a human endeavor. It comes with all the baggage that humans bring to life, and we'll come back to that later. The other component of the book that was interesting to read was your description of how dark matter was discovered. Again, involved very interesting people, yeah. Zwicky and Vera Rubin and Ford. Do you want to share some thoughts on that discovery?
Sure. So I think that the discovery of dark matter, that episode, some of these major discoveries, as Sanjay just mentioned, right, they really reveal the psychological side of science, which is something that deeply interests me. So as someone, because partly I think, and I wanted to emphasize that in the book because, to dispel this myth, science is also a very creative activity. It's a creative human activity, and that scientists are not really dispassionate. We bring our passions to our work. And we are human. We are, as I said, emotionally attached to our ideas. And this whole notion, this sanitized narrative about science and discovery, these scientists in lab coats, they are extracting objective truths from nature, is completely inaccurate. Science as a process is rigorous, but the execution of it, the arrival, the way in which you come to discovery is super messy. There are lots of wrong turns, and you go back to the drawing board, as you know, right? I mean, to me, it is super exciting frustration, but it is frustrating, right? I mean, there are lots of times when you've been calculating, or the computer, in my case, the supercomputer in Urbana-Champaign is calculating for you for months and months, and then you get a result and you just cannot make sense, and you realize, oh gosh, that was a mistake there. Okay, got to start all over again and try to understand this, right? So the discovery of dark matter was really, this is dark matter. It does not emit, absorb, or interact with light at all. But what it does, a la Einstein, because he showed you that matter actually bends space-time, light that is traveling on space-time will be bent around these potholes that all matter in the universe. So the sun creates a little divot, the moon creates a divot, and everything in the universe, anything that has matter creates a divot. And so light, which is confined to travel on the space-time, will traverse all these divots and get bent. And so by the time light arrives to us from a very distant object, it has been bent. And so it carries the imprint of all of that, okay? And so that's sort of one way that Einstein predicted that we should be able to map matter in the universe, whether it's emitting light or not. So Vera Rubin and her collaborators, and Fritz Zwicky, who was a bit of a cantankerous Swiss astronomer in Caltech in the 1930s, he was the first one who realized that the motions of stars in a galaxy, right, the stars are moving around a little too fast. And he couldn't understand that if they were held by their own gravity, just doesn't make sense. They should be flying off. They're moving too fast. What is holding them together? Something that we don't see is holding them together, i.e. gravity. Something that has gravity is kind of, holding them in their grip. And that's when he proposed this idea of dunkel materie, dark matter. And he said there's a lot of unseen matter in order to reconcile the measured. So it's the measurements that you make of the visible matter, that is stars in a galaxy or galaxies in a cluster, that tell you that there's something there that's unseen that is needed to hold everything together. And so, but it took decades before it could be done much more carefully. The instrumentation improved. So in the 70s, Vera Rubin, who was pioneering woman astronomer, this was at a time where women were not allowed to go to telescopes to observe, right? So she was, one of those women who was the first woman to kind of break through that and go out at night to observe in telescopes. So she had this weird data that showed that in nearby spiral galaxies, again, the stars were moving really fast. And it was not just one galaxy, it was a lot of galaxies. So it's not like a one freaky galaxy, you have some matter that you don't see, maybe a lot of neutron stars hiding or something, right? And then the idea of dark matter was proposed. I mean, she was not aware, she had not read Zwicky's papers, so she didn't know, This is another thing that happens in science. People kind of forget the things that, discoveries that are made in the past, and often they rediscover, later on. But she didn't publish the paper. She didn't have the guts to publish that paper for about 4 or 5 years, because invisible entities have a pretty bad rep in physics, right? There was this supposed to be ether, which kind of evaporated, right? There is no ether, because they believed that light also needed a medium to travel. Light, unlike sound, doesn't need a medium to travel, right? So they were very cautious, and they eventually published it, and she's credited with doing the bulk of the work establishing that dark matter exists. Could we go to the next slide? I think I have a slide so that's the light bending that I was talking about that Einstein's theory predicts. So if you have a lot of dark matter, those kind of bent rays of light are the effect of that unseen matter on light, because they are actually this unseen matter is causing a deep divot, a huge pothole in space-time. And so what you see there are Hubble Space Telescope images. On the right-hand side, you see the blue fuzz. That is the reconstructed map of dark matter, which you don't see. Whereas on the left-hand side is what you see. So, and it's the bending of light and the impact of the bending of light. I said, that information is actually carried and transmitted. It's in the distorted shapes of galaxies. See that smiley face? You see all those distortions? Those are not the birth shapes of those galaxies. Those distortions are really distant galaxies whose light has been distorted by dark matter in the galaxy that has those two eyes, right? Those are two galaxies that have a lot of dark matter around them that has bent the light. So using the severity of the bending, we're able to back out how much matter there should be. So that's how we are mapping dark matter. The next slide, please. So this is sort of the work I do. So I'm sort of jumping to tell you what I do myself with dark matter. So what you see in the bottom right corner, that hills and valleys, that is still one of the highest resolution maps of dark matter that have ever been made. And that came out of my work and my research group's work. So those hills and valleys are how dark matter is actually heaped in the universe. It's not uniformly spread out like jam on your bread, but there's a lot of heaping, and this heaping is because of gravity. And those heaps, the crests of those heaps, right, the peaks, are where galaxies form in the universe. So dark matter actually offers the scaffolding on which all the visible matter that we see in the universe actually forms.
That's fascinating. I've just been informed that we are almost out of time. So
Oh
I
my
want to bring
God.
up something else that
gosh.
you have contributed to. And your recent work on the formation of supermassive black holes is a major breakthrough. And if it's confirmed, it would be a remarkable new insight at the very forefront of cosmology. So can you tell us about what this unusual new finding is, and how do you assemble black holes without going through the process of making a star, exploding it, and making a black hole? That's how astrophysicists think of it.
Yeah. So Sanjay just outlined the traditional way of making a black hole. So you form a massive star, it lives out its life and leaves behind a little black hole. So we had started finding in data these supermassive black holes are 1 million to 1 billion times the mass of the sun very early in the universe. So if you started from an endpoint of a star, there just wasn't enough time to grow them billion-fold in the universe, because we roughly know when the first stars start to form. And so you needed an alternative. So with some of my collaborators, with one of my postdocs in 2005 and 2007, we said, well, is there some other way you could make a black hole? And all you need to do is to get a lot of matter into a very compact space. So we found a setting in the universe. Could we just skip a few slides? You just jump through the slides and I'll tell you when to stop. So keep going. Yeah, keep going. Yeah, this is just an Indian connection to black holes. It was a prison, actually. So please go, keep skipping further. Keep going. You can skip all through. Skip. Yeah, please keep skipping. Yeah. Keep skipping, yeah. To the very end, because we are running out of time. Keep skipping, yeah. Yeah, you can stop here. So this is, no, you can go to the next slide. So that was the next one, please. That was the one that the New York Times, yeah. So this is showing you how you can have a gas in the very early universe condense very, very rapidly, and we showed that the physics actually allows this. So before a galaxy forms, it's actually all gas. The universe is basically hydrogen, and so the gas condenses into dark matter. I told you the peaks of dark matter. The gas condenses around it, forms a disk, and the disk starts to go unstable and just starts to break up. It's just like a bathtub when you pull the plug out and the vortex goes in really fast. Something similar to that happens in the very early universe. And you can make these black hole seeds that are about 1,000, 10,000, 100,000 times the mass of the sun from the get-go. So you start with a very massive seed black hole. And so we predicted that, if you keep going, please. We'd made a prediction, a concrete prediction of what this black hole would look like. Remember, you can't get any information out of the black hole itself. I've told you, not even light can escape it. So the way you figure out how a black hole might have formed is the relationship of that black hole to the galaxy that's hosting it. So all galaxies, including our own galaxy, the Milky Way, hosts a black hole in the very center. So Milky Way hosts a 4 million times the mass of the sun black hole. Next slide, please. So we predicted that James Webb Space Telescope should be able to see this peculiar kind of galaxy if it saw a peculiar kind of galaxy with a black hole with very specific properties that we had predicted, then that actually proves that nature makes black holes in multiple ways. So last year, in February of 2023, James Webb Space Telescope actually detected this object. It's called UHZ1. And the next slide, please. And so these are the 4 key properties that we had predicted. And this black hole satisfies all of them. So it's the first kind of evidence, existence proof, that nature makes black holes not in just one way, but in this, these are called direct collapse black holes. And when you see that data, especially the lower plot, I wanted to show you this partly to give you a sense of what we do in science, like what is a prediction, right? So you see that red line, that was a prediction of our model, which we published in 2017. And the cyan blue things with those broad error bars, that is the data from the James Webb Space Telescope. And I fell off my chair when my collaborator sent me the data, and he first joked, and he said, you know, we just sampled. I used this, you know, there's a digital tool called Web Plot Digitizer. He just kind of joked with me and said, you know, I sampled the model you published in 2017. And I said, oh, but why did you sample it? I can give you the curve. We can overplot it. You didn't need to look at a published paper and, you know, try to figure it out. I could have sent you the curve. And then he said, no, Priya, sit back in your chair. That is the data from the James Webb Space Telescope. So it was pretty freaky.
Yeah. Congratulations.
Thank you.
This
it was
is
just super freaky,
exciting.
I have to say.
Yeah.
And I think, you know, as you know, Sanjay, right, in the life in science, right, for those of us who've made that choice, right, of immersing ourselves in a life of the mind, this is the kind of cycle we dream of, right, within one lifetime. And that's what's exciting about science right now, overall, that you can make a prediction, and within your lifetime, it can be validated or invalidated. Of course, it's cooler when it's validated, and, you know, it's much nicer when it's validated, right?
Yep.
So it's just been, it's been a complete dream. So I've just been sort of floating for the past year or so.
Absolutely. Congratulations, and I think we should stop here to give the audience an opportunity to ask us questions. And this was fascinating talking with you.
Thank you so much. Yeah. Thank you so much, everyone.
We have room for one more question after this gentleman here.
Hi. So basically, a lot of this field is very visual, right?
Yeah.
And about 500 million years ago, we evolved eyes. That's when we actually got eyes and we got our vision, and now we can do what we do today, right? To get to the next step, do you think we need another evolutionary change in ourselves to see the next thing, like dark matter and so on? Because we use tools today, right? We use machines, we use AI, we use all of this to put a lot of the things in a lot of minds together that we can't do individually or even in groups, right? Well, what are your thoughts on that?
Yes, it's a great question. So although evolution has made our eyes sensitive to a very narrow range in the electromagnetic spectrum, humans have been clever enough. This is the remarkable thing about us, right? So we have like a gelatinous thing the size of a cantaloupe in our heads, and we've figured all of this stuff out. We've actually made detectors that are sensitive to the electromagnetic spectrum, to the much more energetic light in X-rays and gamma rays, and much lower energy light in radios, microwaves, and in the infrared. So we've already enhanced the visual range, not from within our bodies, but with the detectors that we have crafted. So, I mean, I think when you think about what kind of change in us that is likely to push ourselves to a deeper understanding of the cosmos, I actually think that the inferential power from vast amounts of data that is beyond the capacity of not just a single human brain, but collective human brains, for which we need AI and machine learning, are really going to break open our understanding. And science is going to be done in a completely different way, and discoveries are going to be done in a very different way. So I'm actually super excited and a little nostalgic as well, because I can't, we've moved away, as I mentioned earlier, from the sort of lone male genius model of science to now it's all collaborative. And even then it was collaborative, it was just not acknowledged. But now it is truly collaborative, right? And and you have people working in either small groups or as individuals or very large collaborations. I mean, there's now, there sort of CERN is thousands of people, like the discovery of the Higgs boson. How many thousand, Sanjay? I mean, yeah, a few thousand, right? So I think that the collective creative power, we've figured out how to harness that, but I think combining that with the vast trove of data that is completely unprocessable by anything other than the machines that we've made is an exciting possibility.
Great, thank you.
That's all the questions we have time for in this session. But everyone, please join me in just extending a thank you to Priyamvada and Sanjay.
Thanks, everyone.
Thank you.